Hello guys, we're going to start with 8.2 integration by parts, and this is particularly useful for integrands involving products of algebraic and transcendental functions. So for example, when I have something like the integral of x ln of x, so far we haven't been able to integrate anything like that. Or if I have something like x squared times e to the x dx. Okay, see how we have like an algebraic part and a transcendental part. So integration by parts is very useful for that. We're essentially going to be doing the opposite of the product rule for the derivatives. All right, so let's start with the product rule of the derivatives. So we have u times v. That's a product of two functions, and we're taking the derivative of that. And remember, that's just u times the derivative of v. That's the dv dx plus v times the derivative of u, du dx. And as long as u prime and v prime are continuous, we can integrate both sides. So let's integrate and see what happens here. So I've got the integration, and I'm going to multiply both sides by dx. All right, so everything gets multiplied by dx. So here's what happens. The derivative and the integral, the dx and the integral cancel out on the left-hand side, so we just have uv. And then over here, the dx's cancel on the right-hand side, so I just have u dv plus the integral of v du. All right, and then what we're going to do is just solve for the integral of u dv, and that gives us uv minus the integral of v du. Now that may not seem like much, but we're going to be using this result as a formula for integration by parts. Okay, so again, here's our criteria. If u and v are functions of x and have continuous derivatives, then we have the integral of u dv equals u times v minus v du. Okay, so that's the formula we're going to use throughout all of these examples. So the whole idea here is we're going to be choosing u and dv to represent the different parts of our integrand. All right, so what we pick will either make our lives easier or a lot harder. So here's some guidelines for that. First, you can try letting dv be the most complicated portion of the integrand, but make sure that it fits a basic integration rule. Okay, you want to be able to integrate it. And then whatever's left over will be the u parts. Okay, now a lot of times dv, there is no complicated portion. They're both equally complicated. So when that happens, we focus more on the u. So then we let the u portion be the integrand whose derivative is a function simpler than u. Okay, so when we take the derivative of it, it's more simple than it started. All right, and then dv will be the remaining. So in order to help us do that, we use the acronym LIATE, and that is just symbols for what kind of functions we should pick for u first. So first off, if we see logarithmic, make that u. All right, that's the L in LIATE. And then for the I, that means inverse trig. Okay, so if there's no log, but you see an inverse trig, then make u your inverse trig. If there's neither of those, then you want to pick the algebraic portion. That's just any kind of polynomial like x squared, x cubed, things like that. And then the next thing we would pick for u would be trigonometric, so that's like sine x, cosine x. And then the very last thing we would pick for u would be exponential. All right, so those are the guidelines of using the integration by parts, and now what we're going to do is do some examples so you can see how it works. So in example 1, we have the integral of t e to the t. So according to LIATE, we've got t and then e to the t. T is algebraic, e to the t is exponential, so we would make t the u. And then we would make dv everything else. So dv would be e to the t dt. And if you notice in our formula, we will need to know what u is and what v is, and then I need to know v and du. So I'm going to take what I designated as u and dv, and I'm going to find the du. So I'm just taking the derivative of u. So the derivative of t is just 1 dt. And then in order to get v, I'm going to integrate both sides of my dv. So this is going to be v is equal to e to the t. Now I'm not going to put a plus c here. What we'll do is at the end of our integration, we'll put a plus c. All right, from here, we're just plugging into the formula. So here's our integral. We've designated this part to be our u, this part to be our dv. So we know that this is going to be equal to u times v, so that's going to be t times e to the t. So that's the u, that's the v, minus the integral of v, here's our v, that's e to the t, times du. What's our du? Well, that's just dt. Okay, so we plug that in, and now what we do is we simplify everything. So nothing really to simplify here, that's just t times e to the t. But we have to integrate the e to the t dt, and that's pretty simple, right? The integration of e to the t is just e to the t. Now here's where we're going to put our plus c, and then the back of the book will probably factor out common factors. You see how you have e to the t in both terms. So then we would factor that out. Now, I don't care if you factor, but just be aware when you're checking your answers into the back of the book, they will factor. All right, let's move on. Let's do some more examples. All right, for example 2, x times sine of x. So according to Liate, we should make u the algebraic, not the trig. All right, so u is going to be the x, which means dv is sine x dx. And then what other pieces do we need? We needed the du, so that's just going to be dx. And then we need to integrate the dv to get plain old v. So remember, this is going to be negative cosine. Remember, the derivative of cosine is negative sine. We didn't have a negative. And so we have all of our pieces now to fill in the formula. I'm not going to write out the original integral. I think you can see that this is my u, this is my dv. Okay, so this is going to be equal to u times v, so that's negative x cosine of x, minus the integral of v du, that's negative cosine x dx. So I'm basically just integrating the positive cosine of x. All right, so the antiderivative of the cosine of x is sine x. So I've got this plus c. All right, so that's my answer. This is what that integral is equal to using integration by parts. All right, so let's continue with some more examples so you can see that u, that Liate working. In example 3, notice we have ln, so this is going to be my u, and then these two things are going to be my dv. So u is equal to ln of x, and dv is equal to x to the 4th dx. So my du is going to be 1 over x dx, and my v, remember for integrating this, use your power rule, so that's 1/5 x to the 5th. Okay, so now we're ready to plug into the formula. So this is equal to u times v. So I'm going to bring that 1/5 x to the 5th in front of the ln, minus the integral of v du. So here I've got 1/5 x to the 5th times 1 over x dx. So let's simplify that a little bit. 1 over x and times x to the 5th. That'll just be x to the 4th. And then we're doing the antiderivative of that, which we've already done. So we know that that's going to be 1/5 x to the 5th plus c. And then I'll bring this stuff down too. So I've got 1/5 x to the 5th ln of x in front of that. Okay, so if we simplify that just a little bit more, we'll get the negative 1/25 x to the 5th. And again, your back of the book would probably factor out the 1/25th x to the 5th. Okay, so that would leave us with 5 ln of x minus 1 plus c. And that would be our final answer. All right, so moving on to example 4. We have the integral of arctan of x dx. So this one looks kind of weird because we don't have two functions. So we're just going to follow Liate again, make u the arctan of x, and then that makes dv simply dx. So when we do the derivative, remember your derivative of arctan is 1 over 1 plus x squared dx, and then the integral of dv is simply going to be x. Okay, so not too bad, right? So if we follow up our formula, this is going to be u times v, so that's x arctan of x minus the integral of v du, so that's x times 1 over 1 plus x squared dx. So now we have a more interesting integral. Remember that we would use u substitution here. We don't want to use arctan because we have this extra x here. So, and I don't want to use u substitution because I already have u designated as arctan of x. So I'm going to use w as my substitution variable. So I'm going to call that 1 plus x squared my w, and remember our dw would be 2x dx. So I have the x dx, but I don't have the 2, so we'll compensate for that outside with the 1/2. So this is like 1/2 the integral of w to the negative first dw. All right, so if we integrate that, then we have ln. Remember that we can't do the power rule there, that's just ln. And we could put absolute value of 1 plus x squared, but remember that that's always positive, so that's not really necessary. And then we'll bring down the very first part, the x arctan of x. Okay, and that's our final answer. So moving on to example 5. This is called the tabular method, and you can look at this in your book if you'd like, but it's used to organize your work on an integral that you have to use the integration by parts more than once. So here's an example. We've got x squared, which is algebraic, and we have e to the 2x, which is exponential. So this would be my u, and then this would be my dv. So if let's designate that and go along as we have been, and you'll see what happens when we try to do what we've always done. So we have du is 2x, our v, okay, so think about when we integrate this, okay, this is e to the u, so I also need the du inside my integral, which is just 2. So we would have to compensate outside of the integral with a 1/2. So my antiderivative is 1/2 e to the 2x. Okay, so the formula then would look like u times v, so that's 1/2 x squared e to the 2x minus the integral of v du. Notice that v times du, the 1/2 and the 2 cancel, so I'm not going to write that right here, save some space, and so I'll just have x e to the 2x dx. I forgot my dx here, didn't I? Okay, so here's the problem. I have to do integration by parts again there. So you're welcome to, continue. You could continue this on your paper if you'd like. There's nothing wrong with that. But let me show you how you can do this same problem using the tabular method. So notice in our first column, we just alternate signs. Always start with positive. Okay, positive, negative, positive, negative. And then in the second column, we're going to do the u and its derivative. So u we designated as x squared. First derivative of that would be 2x, and I'm not going to put the dx here. And then if I took the derivative of 2x, that would be 2. And if I took the derivative of 2, that would be 0. And here's where I can stop. The reason is we're going to be doing u times v, right, when we do the formula. And when I do 0 times v, then there's nothing there anymore. So that I know I'm stopped. I don't have to do the process anymore. Okay, so this tabular method really only works as long as your u can eventually come down to 0. Otherwise, it's not going to be very helpful. Okay, so the third column is dv and its integral. So we designated dv to be e to the 2x dx. All right, so the antiderivative of that we already said was 1/2 e to the 2x. Now, if I did the integration of this again, then I would have to compensate again with the 1/2. So I would have a 1/2 for the compensation and also the 1/2 that was already there. So that would be 1/4 e to the 2x. And then if I did the integration again, I would be multiplying by a half again. So that would be 1/8 e to the 2x. And then I'm down to the fourth row, so I can stop there. So here's how this works. The positive goes with the x squared, and then the x squared, remember this is our u, and it always is u times v, and this is the v. So I'm going diagonal here because this is this first one right here, that's the dv. So we don't want to really use that. That's not really useful. So I don't want to cross it out, but it's not really part of what I need. I just put it there as a space saver. All right, so then here I'm going to have a negative times 2x. This u would be multiplied by this v. And it's going to get a negative because it has a negative in front of this. So this part represents this iteration of the integration by parts. So that's why that has a negative in front of it. Okay, and then on the third iteration, we would have a positive because I would have two negatives. I would have this negative, and then I would have another negative nested inside. So that would be 2 times this. And then I can stop there because I don't need to do the 0 times anything. All right, so we match all those pieces up, and this is how we write it out. So I'm going to have positive x squared times the 1/2 e to the 2x. Then I'm going to have a minus 2x times the 1/4 e to the 2x. So I'm going to have the positive 2 times 1/8 e to the 2x. And here's where I can put my plus c. And then we can simplify it. And you probably were already simplifying as you went, and that's fine. So then I have the 2 times the 1/4, and that would be 1/2 x e to the 2x. And then 2 times 1/8 would be 1/4 e to the 2x. And then we have our plus c. This is totally fine to leave it like this. The book would probably factor out a 1/4 e to the 2x. And then we'd be left with 2x squared minus 2x plus 1 plus c. All right, so let me show you this example 6 because this one is also an unusual situation. We have e to the x and sine of x. Liate says trig before exponential. So u is going to be our sine x, and dv is going to be our e to the x dx. So du would be cosine of x dx, and our v would be e to the x. Okay, so I'm going to write this out. Integral of e to the x sine of x is equal to u times v, so e to the x sine of x, minus the integral of v du, so that's e to the x cosine of x dx. Okay, so here's where I have to do it again. So I'm not going to use tabular method, and here's another way you could just use it nested, and you'll see why I'm not using tabular method in just a minute. So I have to repeat this process, so that means I have to pick out a new u and a new dv. So for this time, I'm doing it in green. My u is cosine of x, so my du is going to be negative sine x dx. And then my dv is e to the x dx, so v is simply e to the x. So for the green part, I would have negative in front of all this stuff. u times v. So that would be e to the x cosine of x minus the integral of v du. So that would be negative e to the x sine x dx. And then if I simplify this, this is negative times negative, which is a positive integral, really. And then I'm going to distribute that negative. So since these are both positive in here, really, these are now going to become both negative. I will also bring this e to the x to the sine x down. E to the x times sine x, not to the sine x. And so I want to remind you that our whole goal of this is to try to find what the integral of e to the x sine x is. Well, now I've come full circle and I have to redo this again. So this is why tabular method is not really effective, because my table would be infinitely long because my du's never go to 0. Okay, so I'm going to use a different way, and this is kind of cool. We are going to use these as like terms. So I'm going to add this integral over to the other side so that I have 2 of these integrals. And then those 2 integrals are equal to e to the x sine x minus e to the x cosine x. And then to solve for that integral, we just divide by 2. So the integral of e to the x sine x is equal to 1/2 e to the x. I'm factoring out the e to the x. And then I have sine x minus cosine x. Plus c. Let's act like I put that and I remembered that in the very beginning. Okay, so pretty cool. So there's a trick when your derivatives don't go to 0. You still have to do repeated integration by parts, but you can use that little trick to do that. Last example, this one looks kind of weird. So it might seem a little overwhelming because Lyautey is vague on this. We have algebraic, we have exponential, but we also have an algebraic in the denominator. So it's like, which algebraic do we make it? Would I make it the whole thing? You know, what's going on there? So I'm going to refer us back to the original guideline of let's make dv the most complicated part so that we can integrate it and make it less complicated. All right, so the complicated part of this, ooh, I forgot my dx, didn't I? This should be a dx right here. So the complicated part of this is the stuff in the denominator. So out of all of these things, this is really the monster there. All right, so if I was trying to make dv equal to x squared plus 1 raised to the 2nd power in the denominator. Let's think about if I had to integrate this, because I would have to find v. If I had to integrate this, I would be using u substitution or w substitution, and my w would be x squared plus 1, which means my dw would be 2x dx. So the problem with this over here is that I don't have the 2x, right? So I can borrow, here's the tricky part, I can borrow from this other algebraic part here. So instead of keeping that as x cubed, I'm going to break it up into an x and an x squared. And I'm going to make the x go with the dv. Okay, so we're going to swing that over into the dv part, because that's what I really want over here. Okay, and then the x squared and the e to the x squared are going to be the u part. Okay, I'm going to erase this 2 because I don't really have a 2 over my original integrand, so I don't have that. But that's okay. We can mess with the 2 later when we integrate. All right, but I said we're going to make u, not u cubed, or x cubed, but x squared times e to the x squared. All right, so if I do my du, we have to do product rule. I know you guys are probably hating this already. So I'm going to take the derivative of x squared. That's 2x times e to the x squared plus, keep the x squared the same, and then the derivative of e to the x squared is going to be 2x e to the x squared, all times dx. All right, so that's the u part. Let me section that off so we don't get confused. All right, so over here, v, I have to do the integral. So I'm taking the derivative. Remember, we need the 2, so we can compensate outside with the 1/2. So I'm going to get v is equal to 1/2. This is going to be the integral of dw over w squared, all right, or w to the negative second. So when I do the antiderivative, I'm going to add a power, so that's going to be w to the negative 1, and then I'm going to have a negative out there, right? So basically what I have is a negative 1 over 2 times x squared plus 1. All right, so that's what we have for our v. We have our u and our du, so we're good to go. Now we can use this for our formula. So our formula says u times v. So I'm going to take this times this. So we're going to have negative x squared e to the x squared over 2x squared plus 1 minus the integral of v du. So I have this negative 1 over 2 times x squared plus 1 times du, all of this product rule stuff. 2x e to the x squared plus x squared 2x e to the x squared. All of that has a dx. Okay, so I know it looks horrible, but let's simplify. This is where factoring will help us actually. You see how they have 2x e to the x squared in common? So if we factor that out, that would be 2 to the x e to the x squared times 1 plus x squared. So the reason that's helpful, well, that's in the numerator. This red stuff's in the numerator. So that's going to cancel with that one. And then the 2's are going to cancel. So what I really have in my integral is, well, I've got these two negatives make it positive integral of x e to the x squared dx. And that's a lot easier. All right, this is like our u. Our derivative of that is 2x, so I need a 2 there, compensate outside with a 1/2. Okay, so I've got 1/2 e to the x squared plus c as the antiderivative. And then all of this stuff out here is simply brought down. Okay, and you can totally leave it like this. I'm fine with that. All right, so we've got that. Not too bad, even though it seems very intimidating.